Hi, my name is Tom Hoeffel, and this channel is all about helping students learn chemistry. In this video, we're specifically talking about ionic bonding. Now, in general, there's going to be like three major types of bonding. Okay, the first one that we're going to talk about today is ionic bonding, and that's where you have one element that's kind of like holding onto its electron very loosely. We would call this a low ionization energy, and there would be another element that would just come in and snag that electron. It'd be a complete transfer of electrons. We call that ionic bonding. Okay? The other two types of bonding are going to be covalent, and that's where one element's holding on to the electron and the other element's holding on to the electron, and they're sharing the valence electrons. We call that covalent because they're sharing the electrons. Now there's a polar covalent where one molecule is able to hold on to the electrons a little bit better, and it's an unequal share of valence electrons. We call that polar covalent bonding. And then we have one where they share their electrons equally, and we call that nonpolar covalent. Okay, so we got ionic, where there's a complete transfer of electrons. We have polar covalent bonding, where there's an unequal share of electrons. And then we have nonpolar covalent, where there's an equal share of electrons. And today's video is all about that first type of bonding where there's a complete transfer of electrons called ionic bonding, because when the transfer of electrons occurs, they create ions, and that's where we get the name ionic bonding. Okay, so I have two Bohr models here, one for sodium and one for chlorine. And if we come in here and we investigate the sodium a little bit, we find out that sodium has one valence electron. That means there's one electron on the outermost shell, okay? Where chlorine has 7 of them, okay? 7 electrons on the outermost shell. Now remember, when these guys touch each other, okay, it's going to be those valence shells that actually hit first, okay? And we have this thing called the octet rule, and oct means 8, okay? And I have this little saying of 8 is great like chocolate cake, because when things tend to bond, they tend to fill up their valence shell, and they have 8 valence electrons. So 8 is great like chocolate cake. So when we look at the sodium, okay, you say, well, how does this one get up to 8 valence electrons? It would have to like gain 7 electrons, okay? There's actually an easier way, okay? This electron is actually going to be transferred from the sodium to the chlorine. Okay, and when that electron gets transferred, this is no longer the valence shell. Now this one becomes the outermost shell, and what do you see? You see 8 valence electrons. Once again, 8 is great like chocolate cake, and that's kind of what we have going on with the sodium. So this is going to help with the stability of the atom when it has those 8 valence electrons. And when that electron is transferred over here, this no longer has 7, now it has 8 as well. So both of them are getting a filled valence shell with 8 valence electrons, and we call that the octet rule. Now, when this electron is transferred, this is no longer a neutral sodium. It just lost one of its negative particles. And if you take away the negative part of the atom, what's left over is going to be positive. Okay, the protons and electrons are no longer in balance. Okay, if you take one of the electrons away, you actually have one more proton than electron because that electron has been removed. Okay, so we would say that sodium is now a positive 1 ion. Okay, likewise, the chlorine gained an electron. It's taking in an electron. Before, the protons and electrons were the same and had no charge. But if you add an electron, which is negative, this will become a -1 charge. And this is where this opposite charges is actually the attraction pieces that hold, the compound together. And in this case, we use 1 sodium and 1 chlorine. So we get this 1-to-1 ratio, so the subscripts are 1. And the way we name it is we name the metal first, followed by the nonmetal, and ending it with IDE. So this is going to be sodium chloride. Now, when I look at this, it seems like, wow, there's kind of like a lot of noise going on here. I wonder if there's a better way. I mean, really, the nucleus wasn't really involved in the bonding. core electrons really weren't involved in bonding. It was just these valence electrons that were involved in, the bonding. So maybe Bohr models aren't the best models to use for chemical bonding. And we have this thing called a Lewis dot structure where you write down the symbol. So we got sodium and chlorine, and then we use one dot to represent the number of valence electrons. So if there's one valence electron, one dot. Two valence electrons, two dots. So when we came back here and started this problem, we had one valence electron on the sodium, so it'd get one dot. And then when we started the chlorine, it had 7. Now we want to distribute them as evenly as possible, as if this was a box. So a top, a bottom, a left, and a right. If you have 7 valence electrons and we start distributing them around, you're going to find out when we get to 7 that 3 of the sides are going to be doubled up and one of the sides is going to have the single electron. So this is a Lewis model for chlorine and this is a Lewis model for the sodium. Okay. Well, we're going to transfer that electron over from the metal to the nonmetal, and I am using an arrow here. Okay? If you use just a line, that actually means covalent bonding, which is one of the other types of bonding that exists, of which we will cover in a future video. Okay? So we got to make sure that this has an arrowhead on it to make sure that we're saying, hey, it's not sharing the electrons, it's being transferred over from the metal to the nonmetal. And when you have that transfer, remember, you do have to put those charges in your picture. Okay, now some teachers are going to ask you to add brackets around the ions. That depends on the teacher. I do that if the whole molecule has a charge. Okay, but I think this is perfectly fine for a model for sodium chloride. Just be aware that there are other teachers and other professors that might want you to put a bracket around each of these ions. Okay, so that just depends on your instructor. Okay, so let's kind of practice some of these Lewis models. Okay, where it does ionic bonding that might not be a 1-to-1 ratio. Okay, so for example, what if I wanted to bond potassium and oxygen? Potassium's the metal and oxygen is the nonmetal. So whenever you have a metal and a nonmetal, remember, the metal's kind of like holding its electron out like this because of its low ionization energy. And the nonmetal is going to just take that electron in because of its electron affinity or its electronegativity. Okay? And those vocabulary words were discussed in the periodic table trends video. Okay? So I just want to remind you, some of that's in play right here because sodium it doesn't have a good grip on its electron. And the chlorine over here does a great job of taking in an electron, okay, based on those periodic table trends. But back to potassium and oxygen, okay. If I look at where potassium is on the periodic table, it's in the first column, so it has 1 valence electron. Oxygen is in group 16, and group 16 has 6 valence electrons. So remember, we're going to distribute them as evenly as possible. And if we have 6 valence electrons, 2 sides are going to be doubled up, and 2 sides are going to have a single electron. As you can see, the electrons probably going to go from the one that has only a few valence electrons, the metal, to the one that has a lot of valence electrons, which would be the nonmetal. But when this does this, okay, the potassium is getting the octet rule because when it loses its electron, it's actually showing a new layer of 8, okay? But when that electron is transferred over to the oxygen is only getting up to 7 valence electrons. It started with 6, and when it gains 1, that only puts it up to 7, okay? So what is the answer? The answer is that potassium and oxygen are not bonding in a 1-to-1 ratio, okay? So we're going to need another potassium in order to complete this problem. And that 1 electron is going to be transferred over to the oxygen. So you have 2 potassiums that are creating +1 charges because each of them are losing 1 electron. But the oxygen, because it's gaining 2 electrons, is going to take on a -2 charge, okay? Because it gained 2 electrons. If you add up all these charges, it does have to equal something that is neutral, okay? And the ratio of atoms here is going to be 2 potassiums for every 1 oxygen. Okay, and then we're going to name this. We write down the metal, potassium, and then oxygen. We're going to take off the ending and add IDE. Okay, we don't use prefixes for ionic bonding. Okay, and the reason for that is the 2-to-1 ratio is the only ratio that will work for potassium and oxygen. Whereas over here, the only ratio for sodium and chlorine that works is 1-to-1. So because there's only one ratio that works, we don't have to use prefixes. Prefixes are going to be used for the covalent compounds where they can bond in multiple ratios depending on how they share their electrons. But for ionic compounds, there's only one ratio that works, okay, and that's why we don't use prefixes. So I'd like to wrap this up with just 2 more practice problems, okay, where we're using Lewis models. Let's do aluminum and chlorine. And if we do aluminum and chlorine, we're going to find out that aluminum has 3 valence electrons. The chlorine has 7. And we're going to start transferring these electrons over. I'll transfer this one over first. This one's filled, but this one still needs to get rid of 2. So we're going to draw another chlorine that has 7 valence electrons. And we're going to have to draw a third one that has 7 valence electrons because all chlorines have 7 valence electrons. But if this thing's trying to get rid of 3 electrons and the chlorine will only gain 1 of them, then we're going to use 3 chlorines in order to do that. Each that are going to be a -1 charge because they each gained an electron, whereas the aluminum lost 3 electrons, so it's going to be a +3 charge. So the formula for this is going to be a 1-to-3 ratio, so it's aluminum chloride as its name. And then the last problem I want to do is with magnesium and oxygen. I'm sorry, magnesium and nitrogen. Magnesium and nitrogen, because I think this is the hardest problem that you can get. Okay, so magnesium that has 2 valence electrons, nitrogen has 5. Okay, so if we transfer these electrons over, you can see that this one still needs 1 more. So we do another magnesium. We transfer that over. Now both of these are happy, but this still wants to get rid of 1. So we draw another one that has 5 valence electrons, transfer it over. Now this one's happy, and this one's happy, but this one still needs to gain some. You think this never ends, but if you keep working on the problem, you'll eventually get to a point where all the electrons are transferred over, okay, and all of the ones that have been transferred over will get to 8. These each will be a +2 charge, and this will be a -3 charge. We use 3 magnesiums, we use 2 nitrogens, and the formula is going to be magnesium nitride. If this information helped you learn chemistry a little bit better, please like and subscribe. We want to hit that algorithm so this is shared to as many chemistry students as possible.